So welcome everyone to this data course. My name is Hein and I'm going to take you to this session on flexible parametric survival models. As always, you can find the presentation and data and programs on the home page. And as always, if you have questions or comments along the way, please just interrupt and ask the questions, or if you prefer, type your questions in the chat. So just a few words about the syntax files and the data sets. So there is one syntax file called downloads, and it contains a list of programs that you need to install if you want to use the type of methods that I'm talking about here. Then there is one syntax showing you standard survival analysis using the Cox model. And we will cover just a little part of that. And then the main part of the course will be about flexible parametric survival models. There are also 3 data sets that we will be using a lot. One on melanoma cancer, one on kidney cancer, and one on breast cancer. Again, these are on the home page. So our agenda will be to talk about standard survival analysis, talk about hazards, survival, and hazard ratios. We will present the Cox model, talk about different timescales, and then we will discuss some limitations of the Cox model. And that will lead us to using an alternative to the Cox model called the flexible parametric survival model. And this one relies heavily on splines, so we will define splines, talk about the model syntax, and also the predict syntax connected to the model. Further, we will talk about assumptions of the standard model, proportional hazards, linear dose response, no interactions, and non-informative sensory. And we will only have time to focus on this first one, proportional hazards. But as always, these are assumptions of the standard model, and there are alternatives that we can use. Yes. And then I have one section at the end talking about problems with the hazard ratio. And that leads us to using some alternatives to the hazard ratios. And this could be restricted mean survival time and difference between these, or standardized survival curves. So that is the agenda. This course is based heavily on the book Flexible Parametric Survival Analysis from Royston and Lambert, and also on syntax found on the home pages to Lambert, Dickman, and Crowther. They all 3 have really great home pages with lots of information. So any credit for good syntax goes to these people. Standard survival analysis. I will start by talking a little bit about closed and open cohorts. So here is a cohort of 7 people. Each line segment is 1 person. This one is followed from beginning till end. This one is followed until he had disease, and so on. And this is called a closed cohort. People are coming from the beginning and staying until the end, unless they have a disease or death. And in such a situation, we can count persons and talk about risk. And risk is then number of new cases divided by the number of people in the population. Most cohorts, however, are open cohorts. People come and go a bit more at their own will. So here is one coming a bit late, staying until the end. This one is coming late until he gets a disease, coming late and leaving early, and so on. And in this situation, we need to measure person time. And person time is given simply by the length of each of these line segments. Number of years that that person was under risk or under observation. And that leads us to a rate measure, defined as the number of new cases divided by the total risk time, which the computer can tally up for us. And closely connected to the rate concept, we have the concept of the hazard that we use in statistics. And this is an instantaneous rate, and it's also allowed to vary over time. So it's called h of t, it's a function of time. We also have the survival as a function of time. And then we have effect measures based on either difference or ratio measures of the hazard or the survival. So those are the measures we will talk about. So let's talk about the different measures. I'd like to point out that in a survival analysis, there are always two outcomes. There is the time to event or time to death, and then there is the indicator of event or death, often called small d, lowercase d. I often like to make a plot of the timelines. So here I have just for 3 different people. The first one entered at the start and stayed until the end. He will have a time of 10 years and a death indicator of 0. This one started at the beginning and was followed until 8 years. So his t is 8 years and the death indicator is 1. And this one was starting at the beginning. At 6 years, he was lost to follow-up. So his time is 6 years and his death indicator is 0. So you see, we need both those indicators, so both those variables, the time and the indicator of event. So d equal to 1 is called the event or death, if that's what we're modeling. And those that are lost to follow-up are called censored. We usually start our analysis by doing a survival plot, so-called Kaplan-Meier survival plot. And this is comparing the survival of treated and untreated people over the follow-up of 10 years. At the end of follow-up, roughly 25% have survived, but with a better survival among the treated than among the untreated. We can also plot the hazard functions. So this is the hazard function over time of the treated and this of the untreated. And we have an increasing hazard over time in this example. If you'd like to have an idea of what a hazard means, so a hazard of 0.2, you can get by multiplying it by 100 and saying that this means 20 new cases per 100 person years. So if we followed 100 people for 1 year, we would expect to see around 20 new cases. You can also think of this as an instantaneous risk. So this is that you have 20% risk now of getting disease if you have survived up to this point. Now, this plot shows proportional hazards. And by that, we mean that if you take, say, the green one divided by the red one, 0.1 divided by 0.2, you get a value of a half. But if you do the same comparison over here, you take 0.2 divided by 0.4, you also get a value of a half. So these two hazards have a proportion, fixed proportion between them. And as a function, and as a result of that, the hazard ratio will be a constant, close to 0.5 in this case, doesn't change with time. In general, however, if we are not assuming proportional hazards, then the hazard ratio will be a function of time. Now to the Cox model. So here's the simple description of a Cox model, saying that the hazard as a function of time is a baseline hazard multiplied by a term that we can think of as the hazard ratio. Now, the hazard, as we can see, is a function of time. The baseline hazard is also a function of time, but the hazard ratio is a constant. So this is clearly a model where we assume a proportional hazard. So we have a constant hazard ratio. And the hazard ratio in this case is the exponential of the coefficient over here. And there can, of course, be many more terms in the model, like in B2 times an X2, where we adjust for other variables. Now, we are usually interested in this hazard. In the estimation of the model, however, this baseline hazard is so-called conditioned out of the model. And that means there are no restrictions of the shape on this one. It's a totally free form of a function. Doesn't matter what the form is. And then we are interested in the hazard ratio. And since we have a free form over here, this is often referred to as a semi-parametric model. We have parameters over here, but this one is without parameters, hence semi-parametric. And here we have an example. Here is the hazard rate, this time measured per 1,000 person years. And this is how it develops over time among males and females. And this is taken from a proportional hazard model. If you look at the ratio males over females, it's the same over here as it is over here, although that's not so easy to see. So if we take males as the baseline, we can calculate the hazard ratio by taking females divided by males, and we get a constant hazard ratio of close to 0.6, I think this is. Okay, so that's the Cox model. This was invented by Cox in 1972, and Cox is now late Sir David Cox, still alive, but he's now a Sir. So, and this has been a real success. This model is used a lot in survival analysis. Any questions or comments on this one? So now let's talk a little bit about time scale. Here we have, again, a plot of a number of observations, 10 people that we have followed, and these are dates down here: January 1980, 90, 2000, and 2010. This marks the date of birth. This marks the date of diagnosis, say of some type of cancer. And we are interested in how long do people live after their diagnosis. So the red area, that's the area of interest for us. We follow people until the end of the study, until they're dead, or until they are lost to follow-up. Now the focus here will be on possible timescales that we can use. And the most, yes, I think I've said this. And the most used timescale, I think, is simply time since diagnosis. We're starting time at the red area here, and we're following people, well, for the length of the red lines. We could also use age, if we think that's an important variable, or we could use calendar time. What should we choose? Well, the advice is we should choose the most important timescale, whether that's time since diagnosis or age. That depends on the disease, I suppose. Or you could also choose the one you think is the most nonlinear, because this nonlinearity will go into the baseline hazard, and the baseline hazard is taken out of the model So that's a free parameter. So any non-linearity will be picked up in the baseline hazard. We have a special command for setting the time. It's called stset. And by the way, all survival time commands in Stata starts with st for survival time. So we have the origin. That's when we start counting time. We have the enter. That is when we start being under risk for disease, start of risk time. And we have the exit. So that's the end of follow-up. And we have a failure indicator. So that's the event, death or not. And I'm pointing out here that I think the Stata file is a bit misleading. The help file is a bit misleading here. Maybe it's just me, but I have trouble understanding the way they explain these two concepts. So let us show a few examples of these stset commands. So here we have our data set. Again, this is just three people that I've shown here. So this is the date of birth, this is the date of diagnosis, and this is the date of exit for these three people. This is the event indicator, dead or not. And then I have one variable that's measuring years since diagnosis. If you take this exit minus diagnosis, you get 10.8 years, 12.3 years, and so on. This is the age. It's the age at diagnosis. Now, if we do an stset on this, using years since diagnosis as our time, and dead equal to 1 as our failure indicator, Stata will make three new variables for us. One called underscore T0, that's when time starts, and it starts at 0 for all three. Underscore T is the length of the follow-up, 10.8 years, 12.3 years, and so on. And underscore D is the death indicator, 0, 0, and 1. So this, I think, may be one of the most common setups, that you have a variable measuring the length of the follow-up, and you use that here. You could also measure years since diagnosis based on dates, and that's how we would do that. Then we have the origin of time is at diagnosis. We start counting risk at diagnosis, and we count until the date that you exit from the study. So all these three variables are now dates. And the failure again is the indicator death equal to 1. Now, since dates in Stata are measured in days, we may want to use a scale. And this scale says that we would like to go from days to years instead. And we would get exactly the same result. Based on this, we would get T0 all starting at 0. This would be the follow-up time in years, and this would be the death indicator. If we think that age is a more important parameter than the time since diagnosis, we could use age as our analysis time. And this is how we set it up. So now, instead of having origin diagnosis, we use origin birth, and we use enter time at diagnosis, and everything else is the same. So this is the only one we're changing. The result now is that we get time measured in ages. So this person will be 16 years when he enters the risk, and will be 27 years at the exit. This person will be 8.5 years once he gets on the risk, gets his diagnosis, and 21 years when he leaves, and so on. So playing around with these different parameters gives you different ways of setting up the analysis. And I should say that stset is a very powerful command that can that can accommodate lots of different situations, and it also does a quality check of the data behind the lines for us. So that's quite important to use that one. And in fact, you have to use it as your first command in a survival analysis. Questions or comments about this? Yes. Can you please explain again the T0 in the last model? Okay, so here in the last model, we used dates as variables that we were entering here. We said that origin of time would be at birth, and then we would get under a risk at time of diagnosis, and we would be followed until the exit dates. So all of these are dates. And as a result, you will be 16 years once you get your diagnosis, and you will be 27 years once you exit from the study. This person will be 8.5 years once he gets his diagnosis, and 21 years as he exits from the study, and so on. How do you check that stset has done what it should? Yeah, well, you simply take a look at these variables and see that you get something that corresponds with the dates that you have over here. So this one, born in 82, was diagnosed in 99. So 99 minus 82 is, I don't know, 11, or no, it's supposed to be 16. Yeah, 16 maybe. So my calculation skills are not so good, but you do some head calculations on these dates. And then you look at the time from diagnosis to exit, and or rather take exit minus birth, and you should find that he would be 27 once he exits from the study. So just do a quick check like this. Okay, now to standard syntax for doing standard survival analysis. We usually start by a Kaplan-Meier plot of survival by our exposure or treatment variable. And the command is called STS. We want a graph, and this we would like by the treatment variable. And this says we would like to have a risk table showing us how many people are present at different stages of follow-up. We want to know if the treated or and untreated have different survival. So we can do a log rank test. That's called STS test over treatment. We would like to do a Cox model with one covariate, and that's simply ST-Cox, putting in the treatment variable as our exposure. Notice that we don't need to specify the outcome variables. That's already specified in the stset command. We can predict from the Cox models if we like. Here are predicted hazard curves. So we do ST curve. We want to predict hazards, and this is specifying the contrast or the variables that we would like to compare. So at 1 is treatment equal to 0, and at 2 is treatment equal to 1. Okay, so now let's take a look in the syntax how this is done. So now I'm going to my 5.0 Cox model syntax. I have a path here that says tells data where my data are. So I'm just running this one and can use that as a macro. And when you see the command cd path, that means I'm always looking for the data at this given path. If you want to do this, you just need to change this global path once, and then everything else should be okay. So I say use melanoma. And this is a data set with different stages. We want to only keep stage equal to 1. And we would like to generate a variable called female equal to sex equal to 2. And maybe I should do a describe of the data set as well. So you can see the variables. And you can see we have sex and age. And to our interest is surv_mm. That's the survival time in months. We will use that one. We would need the status variable. That's the vital status at exit. So that's our indicator of event. And we will use the female variable. Now let's SD set the data. So we write SD set. Survival time in months is our time. Failure is status equal to 1. That's the indicator of death. And then we would like to limit the length of the study to 120 and a little bit months. That's because the data is thinning out at the end. And then we would scale from months to years by putting in a scale of 12. Let me run that. And now we see everything that we set up over here. We have 5,300 observations, 960 failures. So those are people dying along the way. And we have time ranging from 0 to a bit over 10 years. Now, I'd just like to show you a timeline plot that I like to do at the beginning. So I just generate an outcome variable y equal to _n. So that's just numbering all the observations in my data set. And then I do a spike plot of _t, that's the observation time from the SDSet command, versus this y variable. And this is what it looks like. So here we see the observation time from 0 to 10 years, and each line here represents a person. So this one died, this one was followed until the end, this one was followed short and was lost to follow-up over here, and then we can briefly look and see that, okay, we have lots of deaths here, and they seem to be spread out over the entire area. We have some people followed all the way until the end, and we have a fair amount of loss to follow up. So that's what we see from this one. So there is a question from Ronnie again. This is the table section I was asking about. The report SDSet produces. For what to look for to be sure that you have not made mistakes. For instance, multiple failures. Yes, well, if you make mistake in your SD setup, or rather, if your data is faulty at some point, then SDSet will report errors. That's why it's a very nice command to have. That's particularly important if you have multiple outcomes or multi-state models, where it's hard to keep track of everything going okay. SDSet will do a great job of looking for errors there. Okay, so this, like I said, is a plot I like to do in the beginning, and you could also add in exposure here if you had some special, rare exposures or time-varying exposures or something. Now to the standard plot and SDS graph, this time by female as our exposure, and we ask for a risk table. And this is the Kaplan-Meier survival plot. We see everyone is alive at the beginning, a survival of 1. Then people are dying along the way. And at the end of follow-up, at 10 years, roughly 75% of the people have survived, and we have better survival among the red, which are the females, than among the males. We can also see that we started out with 2,400 subjects here, 2,900, and we ended up with 500 and something, 900 something. So we still have, a fair amount of people at the end, and that's important. Otherwise, your estimates at the end will be very uncertain. So that's the Kaplan-Meier plot. Now, are the survivals among females different from the males? We do an STS test on the female. That's a log rank test. And we get a p-value of 0.000. So this is clearly a significant difference. Remember that we had a very large data set here. I've forgotten, I have to scroll up. 5,000, more than 5,000 observations in the data set. Now we want to start modeling, and here I'm just showing you a Cox model with just one covariate. So STS Cox and then female. Female is now our exposure. The outcome are given in the SD set. I run this one and I get 5,300 observations, and the hazard ratio for female is 0.63. So any hazard ratio less than 1 means that you have better survival for the females. In this case, well, what is it? 27% better survival among the females, or less deaths among the females. It's significant, and this is the confidence interval for the hazard ratio. Like I said, we could also do plots or predictions from this model. So if I use ST curve, I can predict from the model, and I'd like to predict hazards. I'd like to compare females equal to 0, the males, with the females. So I'm using @1 and @2 to do that, and then I'm adding on some labels here. And from this, we see that hazards are starting out at medium-high levels at beginning of follow-up. Then they increase to about 3 years or something, and then they start declining, but they don't go all the way to 0. And these, I point out again, are not Kaplan-Meier hazards, but predictions from the model. Okay. So that's the baseline or the hazards plots. So you will see a lot of syntax here for the Cox model if you're interested in using that model. But I'm now going back to my presentation, and I'd like to talk about limitations of the Cox model. So first, a few words about the baseline hazard. So there was a question. Please, can you repeat what is in T1 and T2? Thanks. Okay, let me see if I understand that question. Oh yes, @1 and @2, I think you're referring to. So this is my ST curve, my predictions from the model. I want to predict hazards, and I'd like to do a comparison of males and females. So I'm using the construct @1, that's one curve, and that's females equal to 0, which means males. And then I want a second curve, that's the @2, and I set females equal to 1. Did that help, Samera? She says yes already. Great. Okay, so a few words about the baseline hazard. If you're working with, you say, a logistic model or a log risk model, you will get an effect measure that's an odds ratio. In this case, I have a risk ratio. So if people are reporting a risk ratio of 2, then you should always ask, well, what does that mean? Twice the risk of what? And the answer is you should always report the reference or the baseline risk when you have a risk ratio like this one. If your baseline risk is 1 over a million, this means that if you are exposed, your risk is 2 over a million, which is roughly the same. So on the individual level, you wouldn't care. If, on the other hand, your baseline risk is to 10%, then if you're exposed, you would increase your risk to 20%, again, a risk ratio of 2. Well, that's a big difference, and you would care. If you're working with a Cox model, you could report a hazard ratio of 2, and then people or someone should always ask twice the rate of what? And that is twice the rate of the baseline hazard. So my point is you should always report the baseline hazard. Now, since the baseline hazard is conditioned out of the Cox model, it's not so natural to report it, and it's very seldom done, I think. And I think that's a really bad idea. Here is an example of a baseline hazard for the kidney data. This is the follow-up in years since diagnosis, up to 6 years. And this is the hazard. And as you can see from this one, we are interested, are there any hazards very close to 0? This one is not close to 0. But if you have that, well, then you may get very large hazard ratios because you're divided by something close to 0. We also see that this one peaks very early after a quarter of a year or 3 months. So that means that after kidney cancer diagnosis, only 3 months after, you have a very high death rate. And then it declines over time, but does not go all the way to 0. It's still a positive hazard after 6 years. So we have a lot of biological information that we can read of the baseline hazard. And as we shall see, this information in the baseline hazard is not visible in the survival curve. Many people think that if they just show the survival curves, they've shown all the information there. That's not true. There's a lot of extra information in the baseline hazard. Questions or comments on this? Now to some problems with the Cox model. One is that the baseline hazard estimation may be unstable. And by that, I mean that if you have a small data set, you may see a lot of artifacts in the baseline hazards. Another one is that the handling of non-proportional hazards is a bit limited or difficult. And this is something that we should always look at. And the third is that the predict options are, again, somewhat limited. And the margin command after the Cox model is also very limited. So an alternative to this is then to use flexible parametric survival models. And this is a fairly recent invention. This came in the book by Royston and Lambert in 2011. So fairly recent. And if you'd like my short version of why we should use flexible parametric rather than Cox, it is that the flexible parametric and the Cox model will estimate exactly the same under standard conditions, but the flexible parametric models have better options for handling non-proportional models and better predict options. And finally, they are also part of a large universe of many different models that you can expand your ways of analysis. So that's why I prefer these. But of course, this is a matter of choice, a matter of opinion. Let's see, we will do a break pretty soon, but let me show you the splines presentation first. If you've been following these courses, you will see that I have used splines both in the linear and the logistic, and now they will play a special role here in the survival analysis. So the idea is that we need to put in some type of smoother when we have a continuous variable that may have a nonlinear effect over time. The smoothers are flexible functions that can take any shape going up and down several times, something like that. Here is an example of a smoother. Here we have the birth weight as a function of the gestational age in weeks. The green dots show the data. And here we have a smoothing function that is bending a bit up and down and fitting the data very well. So in this case, this is a spline fitted to the data. Smoothers are used, like I said, many places in regressions, but you can think of it here as a replacement for your exposure variable. So assuming now that your exposure variable is continuous and is called X, I'll answer that question in a short while. Then if you're putting in only X in the model, then you are assuming that you have a linear effect in X, either increasing or decreasing. If you're putting in X squared, then you are assuming something that bends one way, either like this or a U shape. And if you're putting in X cubed, then you have something that bends two ways, like this shape. And if you put in all three together, as in a third order polynomial, well, then you have something that's fairly flexible. And even better may be to use a fractional polynomial. Here we have a list of many different polynomials to choose from, and the model will choose the best two out of these 8 polynomials. And this is what you can get. Here is your exposure, here is your outcome, and maybe this will show a shape like this as the result of those 2 polynomials that are chosen. And finally, the method that I prefer, splines, in the version of so-called restricted cubic splines, RCS. Here we start by dividing up our exposure area in segments. And these segments or these divisions are called knots. And between the knots, we will estimate a third order function or a cubic polynomial that fits the data well in this area. Then we will go to the next area and we'll put in another cubic function, and that fits the data well, but we will connect it with the last one in a smooth manner. And in a smooth manner means that they should be continuous, and they shall have continuous first and second derivatives, and that will make them very smooth. And then at the end of or outside the extreme knots, we'll put in line segments, straight lines there, to keep the tails from flipping and flopping about too much. As a result of the restrictions here, we will have just one parameter for what's estimated in this area and another parameter for what's estimated here, and that together will make up the cubic splines. And you could say that polynomials are a bit global in their approach to smoothing, whereas splines are more local. Whatever is going on here is mostly a result of the data over here. Okay, so that's smoothers in regression. As before, we have used smoothers to look at the dose response. That is to look at a nonlinear effect of a continuous exposure. But now we will use them also to model the baseline hazard. So we can have a hazard function that's sufficiently smooth. And we will use them to model time-dependent effects, again, in a smooth fashion. Okay. Then let's take a look at a question from Ronnie. Could you say a little more on timescales? Perhaps put up the slide again and walk us through what choice of age versus time since diagnosis would mean. Okay, let's do that before the break then. Here we go. So it's this one. Maybe I should simply leave the plot or the side like this. Okay, so I started out by saying that we have a data set where we are interested in the effect of a diagnosis, and we follow people from the time of diagnosis to their time of exit from the study, whether that is death or just end of follow-up. So we have a birth date, we have a date of diagnosis, and we have a date of exit. We have an indicator of the outcome, whether that was censored or death. And we have a variable, that's the years since diagnosis. And we have a variable, that's the age at diagnosis. I think the question from Ronnie was, again, how should we choose one variable over another? And that depends. Do you think that time since diagnosis is the most important time scale? And I think for most, say, cancer analysis, that would probably be true. But the alternative is to say that the age at diagnosis is very important. Maybe that's more important because if you get your diagnosis in a high age, that has a larger effect on your survival. So that's one way of choosing. And the other way of choosing is to think about the nonlinearity, and that's probably a bit more difficult. But the point is that whatever you're using as your analysis time will go into the baseline hazard, and that's conditioned out of the model, and you don't need to worry about the nonlinearity. Okay, so here we are doing the same type of analysis. It's years since diagnosis. This one is just based on the variable, and this is based on the dates. And this is showing us time as age, again, based on dates. So these are the two different ways of thinking around this. And I haven't shown you how to do this for using calendar time as the time of analysis. That's not very often done, I think. Okay, then let's take a break and be back at 1:30. Okay, let's start up again. So there was actually a mention here that Sir David Cox passed away last month. I wasn't aware of that. So thanks for that information. So he must have been 80 something old, or maybe even more. Could I please explain the difference between global and local in the smoothing process? So the idea here is if you use polynomials, then whatever goes on in the tail, or whatever this is estimated in the tail, is mostly dictated from the middle here, where you have most of your data. So we have little control over the tails using polynomials. With splines, you have more control of what's going on out in the tails. You can place your knots out in the tails if you like. And the estimation here is mostly determined by the data over here, not so much influenced by what is going on in other segments of the data. Okay, and that's just about this data. Yes. So what we have done so far is to introduce survival analysis in general and talk about the Cox model in particular. And I pointed out a few weaknesses with the Cox model. And I'm saying that we could use flexible parametric models as an alternative. And these rely heavily on splines, and that's why I've introduced splines over here. And splines are used in the survival models in 3 different ways. Let me see. We use it to model the dose-response relationship, as we do in all other models, but also to model the baseline hazards and to model time-dependent effects. So all of these will then use splines as smoothers. And here I will try to show you how that works by showing you some simplified equations. Maybe that helps. So T is time. My exposure variable is called E, and it's a continuous exposure variable. S and a parenthesis denotes the spline, smoothing function. And TD stands for time-dependent hazards, hazard ratios, which is the same as non-proportional hazard or non-proportional model. So I'm trying to show you now what I could call a generic model. It's not a real model I'm showing. I'm just saying that maybe the hazard could be a simple combination of, or a simple equation for the hazard. So I'm using the log of hazard since that's often used, but doesn't really matter. Now suppose that the hazard is equal to a function of time plus a function of the exposure. That means that we are assuming a linear baseline, because this is the function of time. So an increasing or decreasing baseline function, and we also have a linear effect of the exposure. If we replace this function with a spline in time instead, then we have a flexible baseline, and that's what we're doing in these models. Now the shape of the baseline function could be any shape you like, or almost any shape you like. Now, if we don't think that we believe in a linear function of the exposure, we can replace this one with a spline in the exposure variable. So now we have a flexible dose response, like we did in the linear and the logistic models. If we don't think that the effect of the exposure is the same over time, we could add an interaction term between time and exposure. So this one is saying that we have a linear interaction. So either the effect of exposure is increasing linearly over time or decreasing linear over time. But this is then a non-proportional hazard model. And then finally, we can replace this interaction term of T with a spline in T. And now we have a flexible time-dependent model. So splines are used for modeling the baseline hazard. They are used for modeling the dose response. And they are used for modeling changes in the effect of exposure over time, which leads to a flexible time-dependent effect. Okay. Not sure if this was helpful for you, but it helps us think around this. Now I'm just going to show you the equations for the flexible parametric models. And by the way, they are also called Royston-Parmar models. So they do a model in capital H of T, which is the cumulative hazard. And they're saying that the log of the cumulative hazard over time is a baseline function, which is a spline in the log of T, plus a term or a set of terms that are linear combinations of the exposure and covariates in the model. So this is the proportional hazards model. But if we add in an interaction term, and now using a spline in log of t multiplied by e, we get a flexible time-dependent model. So what we need to specify then are the number of splines, that's called the degrees of freedom in the baseline hazard. And if we're having a term like this one, the degrees of freedom for the time varying coefficient. So df stands for degrees of freedom and is simply the number of spline terms. And TVC stands for time varying coefficient. Okay, questions or comments to this bit? Then let's take a look at the syntax for the flexible models. The syntax is called STPM2. ST again stands for survival time, PM for parametric model, and this is version number 2. And then, exactly as in the Cox model, you list your variables. The first one is your exposure, and the others are variables you adjust for. Then you ask for a scale of hazard, because we are working with a hazard model. And then you're specifying the degrees of freedom for the baseline hazard. And this says 2 degrees of freedom, meaning we are using 2 cubic splines to model the hazard, which is pretty flexible. There is no TVC term in here. This means that we are assuming a proportional hazard model now. And then I have a few questions that I'd like to answer in a little while. How many splines should we use for the baseline hazard? And how does this flexible model compare to the Cox model? And we will go to our syntax to answer that. Just point out, if you're an R user, then this is also modeled in R as the flexserve command. And in case I haven't said that, STPM2 is not a part of the Stata commands. You have to download it. And my first syntax called downloads shows you how to do the download. Very easy to do. Okay, now let's try this out in the syntax. So now I go to my second syntax file, flexible parametric survival. I again tell Stata where my data files are found, and then I read in the melanoma data this time. And I do a description of the melanoma data here. So we have again surv_mm, survival time in months. We have status, the vital status at exit, and that's pretty much what we need here. So now I SD set my data as before. Survival time in months is the time. Failure is status equal 1. We limit the time to 120 months, and we scale to years. And if we do this, we will see 5,300 observations and 960 failures, and times ranging from 0 to 10 years, give or take. I can do the Kaplan-Meier plot now with no covariates, just STS graph. And here we see that survival is fairly good. Around 75% of people survive more than 10 years after their diagnosis of melanoma skin cancer. Now let's do a model. I should do this slightly larger. So I do the flexible parametric model, no parameters or no variables for the first model. hazard scale, and I do just 1 degree of freedoms for the baseline hazard. In this case, that means that I get a straight line for the hazard. So that's the same as a Weibull model if you're interested. So that's a very limited or very restricted model. So the point is to show or to see how this estimates on the data. So I run the model. There's nothing interesting to see in the output. I only get my 1 spline and a constant term. No variables were estimated. But I would like to predict from the model, and I will show you the predict sentence in a little while. For now, let's say that if you use predict, you can predict survival into a variable called S1 by this sentence, and your hazards into a variable called H1 by the predict sentence. So I do both of these. Now I can compare the survival plots. If I do STS graph, I get the overall survival that I did up here. Then I do an add plot where I put in a line plot of my S1, the one I predicted from here, versus underscore T, the analysis time. So that will be the survival plots. So the blue curve here is the Kaplan-Meier survival estimate, and that's very flexible, so you can consider that correct. And the straight line here is the survival function that we predicted from our model with only 1 degree of freedom. So a very, stiff model, if you like. So it's an okay fit. Now let's take a look at the hazards. I do STS graph and ask for hazards, and this is just how the smoothing is done. I do an add plot, and this time I plot in my hazards versus analysis time. And in blue here, we have the smoothed hazards, and you can think of this one as the correct one. And over here, we have the hazards from the model, and it's, of course, an absolute terrible fit. So take-home message, using just 1 degree of freedom for the splines is not very good. Although surprisingly, I mean, if you look at this fit, it's absolutely terrible. But for the survival, it's quite okay. And that's maybe a surprising result here. Okay, so using 1 spline for the baseline hazard, resulting in just a straight line, is not enough. So let's now move up to 2 splines instead. And I often refer to these models as PH2 for proportional hazards with 2 splines. So now I do exactly the same, but with 2 degrees of freedom. I predict survival into S2. I predict hazards into H2, and I do the same graphs. Let me do all of them at once. And let's take a look at the survival curve first. I also put in the knots from the splines here, and that's returned by this SDPM2 function. So there's 1 spline in this area and another spline in this area. And as you can see, the blue and the red curves are identical, so we have a perfect fit for the survival. What about the hazards? Here again, the blue line is the same hazard that we saw previously. And now the red line is the hazard from the model. And now you can see it does a very good job of fitting this spline curve. In fact, there's a bit of wiggling at the end here of the smoothed hazard function. And you may or may not believe that as real. Maybe you prefer the red curve that's more smoothed, the one that we're predicting from the model. Okay. So as an advice, I usually say use between 2 to 5 splines for the baseline model. Fewer splines if you're in a small data set, more in a large data set. If you want to see more about this, there is a section called Compare Fit by 1 to 6 splines towards the end of the syntax that you can look at. Is it correct to use AIC and BIC to compare the fit? Yes, you could do that. Here I simply use the graphs of the plotted or of the estimated survival and hazards instead. But you could use that. Okay. No, we're not going back quite yet. So the second thing I'd like to show you is that the baseline hazards from the Cox model may be a bit unstable, or they wiggle a lot. To do that, I need a small data set. So I'm using the kidney data this time. And just to remind you, this data set is already ST set. And we have 350 observations and 322 failures, 6 years of follow-up. We could do the Kaplan-Meier plot for reference. Now you see that there's very bad follow-up or survival after kidney cancer. At 6 years of follow-up, very few have survived. I'm not quite sure what the number is, but it's a very low number. We can now model this with the flexible parametric model. And we have a treatment variable that we would like to estimate. And we're using two splines for the baseline hazard. And we ask for E form so that we get hazard ratios rather than coefficients. And this is what we get. 347 observations, the effect of treatment 0.74, meaning that the treatment have a better survival than the untreated, since the value is less than 1, roughly 26% better survival among the treated. Here are the two splines for the baseline. They don't tell us much, but we can just see that two splines are used. Okay, I will save the estimates from this one as a PH2 model. And I will also predict the hazards. So I predict H0 at treatment equal to 0, and that's the hazard. So that will be the baseline hazard. And then H1 is for the treated group. So this will be the baseline of the hazards for the untreated and the treated. Now I'd like to compare this to the Cox model. So I run ST-Cox treated or treatment. And I get a very similar estimate of 0.74, 75, maybe if we round it off. So this time 25% less death among the treated. Here I do a table of, and I store this one as the Cox model. Now I compare the estimates in this section. And the Cox was 0.75, the flexible parametric 0.74. These are the standard errors. And as you can see, for all practical purposes, these are exactly the same estimates. And if you did this on an even larger data set, you would get exactly the same estimates, or at least for 2 decimals. Now let's take a look at the hazards for the treated and the untreated. So we do an ST curve. That means we are predicting from the Cox model. We're asking for hazards, and we'd like to compare the hazards at treated 0 and treated 1. And then we do an add plot, and we put in a line plot of the two hazards from the flexible model versus _t, the analysis time. So that gives us a comparison of the two baselines and the two, okay. Not quite sure why I got this. This is obviously wrong. Let's try again. Here it is. So in the thick lines here, we have the hazards from the parametric model. This is a hazard among the untreated, and this is among the treated. And in the thin lines, we have the hazards from the Cox model. Again, red treated and blue untreated. No, the other way around. Blue treated and red untreated. And what you can see is that hazard from the Cox model wiggles quite a bit up and down. And here we clearly have some artifacts towards the end. There's no reason to believe this curve. This is an artifact. We believe much more in the curve from the parametric model. So this is an example of the parametric model estimating better hazards than the Cox model in a small data set. Questions or comments about this? So we've already concluded that the baseline hazard is very important, has important information. We should always show it. And then it's a bit of a setback to discover that the Cox model may be a bit unstable. And this is one of the reasons why we might prefer the flexible parametric models. Here I'm showing you the baseline hazards from the parametric model alone. And it's the curve that I've shown you before. We see from this curve that we don't have any areas where the hazard is close to zero. We see that at 25, after 25, half quarter of a year, the baseline will peak, and then it drops to a lower value, but not to zero. So as I told you, a lot of biological information in this baseline hazard that we cannot see from the Kaplan-Meier plot. Now the Kaplan-Meier plot got lost, so let me run it one more time. Here, can you tell the information that we saw in the baseline hazard from this curve? Well, I cannot. It's not possible to infer that things are happening very fast at the beginning, and then that the hazard is dropping off. So there is quite a lot of more information in this one than you can see from the survival curve. So to sum up so far, I've shown you that in choosing the number of splines for the baseline hazard, 2 to 5 splines is okay, more if you have a large data set. When we're comparing Cox to the flexible parametric model, well, we get the same estimates under standard conditions, and the baseline hazard contains a lot of important information. It's something that we should always show. And the Cox can be a bit unstable in small data sets. And then there is a question. Is it also useful to show the treated hazard or just the baseline? Well, that's just a matter of taste. If you have a if you have a proportional hazards model, the two curves have the same shape. So if you have a non-proportional models, then maybe showing both of them is important. From a proportional model, you can show both or just one. It's a matter of taste. So are there any assumptions to use the parametric survival model? Well, not really. So like the Cox model, we are at least in the standard setup, assuming a parametric, a proportional hazards. And then we have the standard assumptions of, no interactions and a linear dose response, all of which we can relax. And we have the standard assumption of no informative missing. So the same assumptions that you have in the Cox model. So they're not very different in that respect. Now, a few words about the predict command. So one thing I like about these flexible models is that you have a very powerful predict command. So I'm starting now with a proportional hazards model. And from that model, I can predict survival. So this is now not a Kaplan-Meier plot, but predicted survival from the model. And you can do that at specific variables, or you can also have so-called standardized plots or standardized to a population. You can also have measures of survival difference, the difference between these curves and how it evolves over time with confidence intervals. You can predict the hazards, and you can predict the hazard difference. And as you can see, we have the largest difference here at around 2 years, and then it decreases again. And of course, you can predict the hazard ratio. And since we are in a proportional hazard model, that hazard ratio is just a straight line, not a function of time. In addition, we can predict things like the restricted mean survival time and more, and we will come back to that. So here is our model again, STPM2 of treatment, a hazard model with 2 degrees of freedom. We can predict survival by saying predict survival and have a new variable called S. Notice that this will predict survival by treatment. It's not a marginal prediction like we're doing in the marginal command. This will predict survival for the treated, if you are treated, and survival for the untreated, well, if you are untreated. We can predict survival differences into a new variable called ST. And this says that our survival difference 1 is to compare treated 1 to something. And that something is always the reference of 0. So we don't need to put in survival difference 2 in this case. It's always 0 at the reference. And this is with confidence intervals. We can predict hazards by hazards command. You can also put in per 1,000 person years to scale the hazard. And again, this is hazards by treatment, since treatment is in the model. We can predict hazard differences. So age difference 1, treatment equal to 1. And again, this is always compared to the reference of 0. And finally, we can predict hazard ratios. Hazard ratio numerator is treatment equal to 1. And then the denominator is, again, always 0. So I don't have to put that in this case. However, when we have more variables in the model than just treatment, we have to specify both the numerator and the denominator. Let's see, there is a question. Can we predict transition probabilities of going from one state to another using this? Yes, these are the hazards are transition parameters going from alive to dead. So we don't have any more transitions here. But if you were in a multi-state models, well, then you would predict transition probabilities or rates. And then there is actually a lot of more. So the prediction options are really quite strong for these models, which is why I like them so much. Yes, you were thinking about multi-state models? Exactly. Well, let's try out some of these prediction in practice. So we are using the kidney data again. This is our model with treatment as the exposure. And here we can predict survival. Now I will use a slightly different form. Now I would like to predict survival for the untreated into S0. So I'm writing at treatment equal to 0, and I want survival. So this you can think of as a counterfactual prediction, if you like. So everyone is set to treatment equal to 0, whether they are treated or not. It's a counterfactual prediction from the model. And here we do the same for the treated. And then I can do a line plot, S0 versus analysis time, and S1 versus analysis time. And you get the plot that you, well, maybe haven't seen before. This is the survival for the treated and the untreated. And as you can see, the treated have better survival, although the difference is getting quite smaller towards the end. This is just showing you if you predict without specifying the variables, then you will get one survival for the treated and another one for the untreated, and you can plot in the same way. Here is survival difference, here is hazard and hazard difference, and let me show you the hazard ratio. I predict the hazard ratio by specifying the hazard ratio numerator equal to treatment as 1 with confidence interval. And I can predict from this one. And it's a straight line because we have proportional hazards model. So Ronnie wants to know, all this stuff also applies to risk analysis. Yes, I'm not quite sure what you mean by this, Ronnie. So where the endpoint is cancer diagnosis. Oh yes, of course. My examples were all about using diagnosis as the start time and then death as the endpoint. But the question here is, does this also work for, say, some risk factor in the environment and cancer as the outcome? And yes, that's can be used for that as well. Okay, let me just show you what you do when you have more than one covariate in the model. And for that, I will use the melanoma data. And now I will use a variable called year 8594. Let me just show you what it measures. So people who are diagnosed before 1984 have the value 0. Those diagnosed later have the value 1. And we're interested in how does the survival depend on when you are diagnosed in time, in calendar time. We also adjust for sex, use scale hazard and 4 degrees of freedom just for fun this time for the baseline hazard. And we see that those who are diagnosed after 1984, 85, have a better survival, hazard ratio 0.76, so 24% better survival. And as before, being female is better, hazard ratio of 0.62. Now the question is, how can we predict from these models? And let me show the survival first, maybe. I can now predict the survival for those who are exposed by putting in at year equal to 1 and female equal to 1. And I can contrast to those who are unexposed. Now year is set to 0, but female is still kept at 1. So my contrast is between year 1 and year 0, right? And I can plot this. So now I have an adjusted or conditional survival curve, if you like, comparing, in both cases, females with diagnosis before 84 and those with diagnosis after 84. And we have better survival for those. And let me show you the same thing for the hazard ratio. I predict the hazard ratio. I set my hazard ratio numerator to year equal to 1 and female equal to 1. And I contrast that to the denominator, year equal to 0, and again, female equal to 1. So the contrast is again only on the years. And I can just do a list of this one because this will only be a number. And we get the number 0.76. So no surprises here. This is the same number we got before. Okay. Any questions or comments about the predictions that I've done so far? Then let's take a look at the so-called out-of-sample predictions. When would we like to predict outside of the analysis times that we find in the data? So there's a question here first. We can also include covariates like regression models. Yes, so these are very simple data sets where we only have one exposure and maybe one covariate that we're adjusting for, but it's just like in any other regression model. You will normally put in lots of variables that you adjust for. And if you do, maybe that was the question, then you have to make a long list of variables over here and a long list of variables over here, or maybe over here in the numerator and denominator, specifying the values for all your variables. So how is age taken into account? Well, this isn't really a proper analysis. You would clearly want to adjust for age to get a proper effect. So then you would add age to your list of variables over here. And when you predict, you would have to specify an age for your prediction. And then later, I will show you how to predict standardized survival curves, where the curve is standardized to the age distribution in our population. Can you only adjust for factors then? Not quite sure if I understand that question. Do you mean only factor variables, or because age is a continuous variables? I think, Claudia, you have to explain a bit what that question was about.
Yeah, can you hear me?
Yep.
Yeah, I was just meaning, because you have female equal to 1, how would you do continuous variables?
Yeah. So suppose we added age to the model. We add age to the model up here. And then when we're specifying down here, you would have to fix age at a given number. So suppose you have ages between 40 and 80 years. Maybe you would like to fix age at 60 years. So you put in age 60 here and age 60 over here, so that the only difference is in your exposure variable. Did that answer your question, Claudia?
Yes.
Yeah, thanks. Okay. Then where are we? Out-of-sample predictions, yes. When would we like to do predictions that are different from the time scale that's in our data? Well, if we have a very small data set, we might want to do that to get nicer plots, because maybe some times are missing in the data and we would like to have a nice continuous plot. And the very opposite, if you have a very large data set, then you can speed up predictions by predicting only on a smaller set of time variables, time values. And finally, you may want to predict beyond the observed time. So that's really out of sample predictions. And maybe also make a table of results. So here is our model, STPM2. We have the year of diagnosis and female as the covariates, hazard scale, 4 degrees of freedom. And now we specify a new time variable. I call that variable T2. And the range command in Stata says that this gives me a new variable ranging from 0 to 20 years, and it will give me 100 distinct values. So T2 from 0 to 20 years and 100 values. And then to predict, I do a predict. I want survival, put it into S0. 0 means set all variables to their 0 values and predict on the new time variable T2. Now, if you have a data set like we have here of 5,000 observations, we instead only predict on 100 values, which is much faster. Only think that all covariates must be specified when you're predicting on a new timescale, otherwise this makes no sense. So that's why I'm predicting for everything set to 0, or you have to specify all covariates to a certain value. Let's take a look. Yes, I'm using the melanoma data for this. That's maybe the same as I had before. This is my model with year and female in the model. Now I want to have a new time variable ranging from 0 to 10 years. And I'd like to have 101 values. That's just to keep the values nice. Doesn't really matter. So that way, let me show you what happens first. Now I go to the data. And at the very end of my data, I should have my new time variable. Here it is. So this one, T, is now ranging from 0 to 10 years, and that's over 101 observations. So instead of predicting on all these times in the data set, ranging from, well, up to 5,000 or almost 6,000 observations, I'm now only predicting over these 100 nicely spread out observations or times. I predict survival, set all covariates to 0, and predict on the new time variable T. And then I can do a line plot of S0 versus T and have a very quick and nice plot. So the idea here is simply to save time when you have a large data set. You can also predict beyond the observed time. Here I set my range to 0 to 20 years instead. Again, 101 observations. I call the variable T2. And now do everything the same, and I can do a plot. Now I have the survival up to the observed 10 years, and then I have simply extrapolated that into 20 years. Now, you may, of course, question whether that is meaningful or not, but at least you have the possibility to do so. Questions or comments on this? Oh, this was a difficult question. If we are using large longitudinal data, measures are generally collected every 2 waves. So if I use waves 1, 2, and 3 as the time variable, how should I specify the time? Every 2 years, yes. Well, this depends on what you choose as your analysis time, because the time we are talking about here is always the analysis time. So if you have set up wave ranging from 1, 2, and 3 as your analysis time, which is a bit strange, but it could be done, well, then you simply put in 1, 2, and 3 as your times. If you have calculated a time instead, So your time will be, well, 0, 2, and 4 years. Well, then you use that time variable instead. But it depends on how you're setting up your analysis type. And just to show you how we could make a table of results, here I have a T tree ranging from 1 to 10 and I want 10 values. And then I do a prediction of, what is it? Survival differences. And I can just display some of the results here. So here I'm showing you for time 3, 5, and 10 years. Here we have the survival differences with confidence intervals. So producing a table of results for whatever you're interested in is very easy using a new time variable. Okay. I think that was, let me just see. Yeah, back to the presentation. And now we're on to the assumptions of the standard model, but then I think we will take a break first, and we will be back at 2:30. Okay, so welcome back. Just one comment on the last question about when time was measured in waves 1, 2, and 3. If you don't have the exact time when an event is happening, then you should probably use an interval censored survival model. And you can do that in these types of models. And I seem to remember that the newer data versions also can do that for Cox models. Okay, so we used the last session to show to introduce the flexible parametric models and to show the very powerful predict options. Now we're on to the next very powerful feature of these models, namely the ability to handle non-proportional hazards. So the assumptions of the standard model are that we are using proportional hazards, that we have a linear dose response, that we have no interactions, and that we have non-informative censoring. And we will start with the proportional hazards assumption. So non-proportional hazards is the same as a time-dependent hazard ratio. And here is the difference. Here in the proportional model, we have the hazards for males and females. And if you take the hazard ratio, comparing males to females to males actually, well, then you have a constant hazard ratio over time. Now, this is an assumption that we are enforcing on the data, and it may not be correct. And if we're relaxing that assumption, allowing for non-proportional hazards, then we may see that the hazards behave differently. And we can then get a hazard ratio that is varying over time. For this example, there is no significant difference between the models. The straight line here is the hazards from the proportional model, and the curve here is from the non-proportional one. But here you have a choice. I mean, do you prefer, or do you have theoretical grounds to prefer the non-constant hazard ratio over the constant one? Well, then you're free to do that. At least you have the possibility to do it. So we have used splines to model the baseline and to model the dose response, although I haven't shown you that yet. And now we will use splines to model the time-dependent effect. So just to remind you about this setup again, T is time. We have a continuous exposure variable. S and a parenthesis denotes a spline, a smoothing function, and TD denotes time dependence. So if I'm only using a model like this one, I'm assuming a constant hazard and a linear, a linear hazard and a linear effect of the exposure. If I'm putting in a spline here for the time variable, well, then I can have a smooth or a flexible baseline. If I'm putting in a spline for the exposure variable, I can have a flexible dose response. And if I put in an interaction term between time and exposure, then I have a time-dependent effect or a non-proportional hazard. This one saying that the effect is linearly increasing or decreasing over time. And if I put in a spline instead, then I have a flexible time-dependent model. And that's what I'm going to show now. I'm going to skip the rest of these. So well, maybe only point out that to put this in, I put in a TVC term listing the variables that have these interactions. And I put in a degrees of freedom saying how many splines I'd like to use for the time-dependent effect. So the word TVC stands for time varying coefficients. And I'm going to start by showing you how this is done in the Cox model. So what you do in the Cox model is to, of course, have the ordinary Cox statement. And here, if you have a variable that you would like to use a time-dependent effect for, you write TVC, name of that variable. And then you can put in an expression for the time-dependent effect. If you put in just _t, well, then you have the model that I showed you earlier, linearly increasing or decreasing effect of the exposure over time. More interesting might be this one. _t larger than 5 will give me a step function. So here is the effect before 5 years, and here is the estimated effect after 5 years. You can also put in a log of time, and here is my best impression of a log function. And if you're not satisfied with this, you can use an st-split command, where you split the analysis time up in small segments. And in each segment, you assume a proportional hazards model that is a constant effect. So we would get something like this. Here I've split everything up into 6 segments. And this is the estimated hazard ratio for the first segment, this for the second, and so on. Now, doing an st-split, of course, means that you increase the size of your data by 5 or 6 or 10 times, and may be a bit problematic to use for very large data sets. And then enter the, well, I'm showing you the syntax here under the Cox model. Now, how can we do this in the flexible parametric model? Well, here is another version where they really shine. We put in TVC and list the variables that should have interaction with time or vary over time. And then we put in a spline and saying we would like to have 2 splines to model the time varying coefficient effect. So 2 splines for this. And then we might get a very flexible effect. And this is now the hazard ratio, how it is changing over time. So here is the proportional hazards model again. Here is the non-proportional hazards, where we're putting in 2 extra terms. We would like to have a time varying coefficient for sex, and we would like to have that modeled with 2 splines. How do we test for non-proportional hazards? Well, this is the standard method of doing it. You fit the proportional hazards model, and then you do a plot of so-called Schoenfeld residuals. And then you look at that plot and decide if you need to add any time-dependent effects. Now, understanding Schoenfeld residuals is not easy. The plot is difficult to read, and it's on a totally arbitrary scale. Again, you find the syntax under the Cox model syntax. The much easier method is using the flexible parametric model. Just add TVC terms for the exposure. And if you like, you can test proportional hazard versus the time-dependent effect with the likelihood ratio test. And then the really great thing, predict and plot the hazard ratio, and then you have exactly what you want. Your real question is, does the hazard ratio, or is it constant over time, or does it vary according to a curve? And then if you have a curve with confidence intervals, you have a straightforward answer for that question. And that's absolutely the best answer you can give. So forget everything about Schoenfeld residuals. Straightforward predictions from this model, much easier. Let's see, I think maybe there are a new message here. Yes, so there's a question from Claudia. How do you choose the number of splines for the time-dependent effect? And that's easy. I usually use 2 splines. I don't expect that time-dependent effect to be very complicated. I think it would be a very strange model where the hazard ratio, goes up and down in a very complicated pattern. So 2 degrees of freedoms, I think, is generally enough. And then there's a question I'm asking myself here. Do we need to put in time-varying coefficients for confounders? And I'll try to give you an answer when we look at the models here. So now let's try this out in practice. So I'm starting with my melanoma data again, a large data set with more than 5,000 observations. And I'm showing you first the proportional hazards model as a reference, with female as the only exposure variable. I'm doing the predictions and I'm plotting hazards for males and females. We've done this before, so this is just to remind you. And I'm also plotting the hazard ratio, which for this model is a constant variable with a value of 0.63. Now let's go down to the non-proportional hazards model. So now we would like to have the effect of female. We allow that effect to change over time. So we put in TVC of female, time varying coefficient of female, and we would like to use 2 splines to model that effect. I store the estimates as TD2, and let's run it and look at the results first. So here we see the effect of female. Here we see the 4 splines for the baseline hazard. And here we see the 2 splines used for the time-dependent effect of female. Again, we cannot really interpret these splines, but we can compare models using a likelihood ratio test if we like. Likelihood ratio test, testing the proportional hazards model up here versus the time-dependent model down here. And we get a p-value of 0.10. So not significantly different models, meaning we don't really need to put in that time-varying coefficient. But like I said, if we have theoretical grounds for doing it, we might well do so. So we will do it, of course, to show how it's done. Now I'm just keeping that p-value for later. And then I predict hazards, and it's exactly the same predictions as in the standard model. Hazards at 0, hazards at female equal to 1, and the hazard ratio comparing female equal to 1 to 0. Now I can do a plot of the hazards in this situation. And here is what we get. Let me see, I can quickly compare to the previous hazards. Here is the proportional hazards model, and here is the non-proportional hazards model. And you can see that we get slightly different hazards over time. What about the hazard ratio? How does it look? We can do this, and here we see 0.63. That was the estimate from the proportional hazards model. And here we see how the hazards change over time with confidence interval. We had a p-value of 0.10 from the likelihood ratio test. And as you can see, the straight line is inside the confidence intervals for the curved line here. So those two are sort of corresponding. Now it's really up to us. Do we want to use the curved model or not? My point is that if you see the shape of the hazard ratio over time, that's exactly the type of answer you would like to get. No more difficult Schoenfeld residuals. This is the real answer that we would like to see. Okay, questions or comments so far? So I'm just going back to summarize what we've done. So we have now looked at the effect of sex on melanoma survival. We showed that if you have a proportional hazards model, well, then that leads to a constant hazard ratio. I think I've said that lots of times during this talk. But if we allow for a non-proportional hazards model, that's a more relaxed model, if you like, then we get time-dependent hazard ratios. Next, we would like to look at time-dependent hazard ratios for age. So we are then pretending for a while that age is our exposure variable. And we're also asking, are the sex estimates the same if we're adding in time-dependent effects for age? So if age is instead a confounder, does it matter to put in time-dependence effect for that confounder? And then also we get into a trouble of very large hazard ratios because we have hazards very close to zero in that estimation. And we handle that by plotting over a restricted range, or we could instead plot hazard differences. Or, okay, I didn't put in anything else. Yes, so let's try that. Sorry. So now I am using the same melanoma data as before. Let's just run it again. Now I have a variable that's called age group, and I'd like to put in age group with a time varying coefficient. Then I need to have dummies for that one because the model doesn't allow this I dot notation. So doing a tab of this one and saying generate age group will make new dummy variables for us. Let's see. Here is the original age group, and here are the new dummy variables, age group 1, 2, 3, and 4. For the categories 0 to 44 years up to more than 75 years. We will use 2, 3, and 4 in the model, meaning that the first one will be the reference category. So there is a question here. If the assumption of a Cox model is violated, does that mean that we should use the non-proportional hazards model? Or do you have suggestions about the solution? Yes, I think if the violation about the proportional hazard is violated, that means that you have a hazard ratio that is varying in time, and I think you should show that. Yeah, I think I'll leave it at that. There's always more to say about things, but let's not get too difficult. Okay, so now we have the age group dummy variables, and we put them into the model. STPM2, female, year, and age group 2 to 4, meaning that the first one is the reference. Now, this is again the proportional hazards model, but we will soon relax that assumption. And then I'll just show you the prediction of the hazards for each of the groups and that plot. I won't go into details here, but this is the very nice plot showing you. Here is the hazards for the oldest group. They have the highest hazards, and this is the youngest group. So we have a nice distribution over age for the different hazards. But they are proportional. There's a fixed proportion between each of these curves. Now let's relax the proportional hazards assumption by putting in a TVC term, time varying coefficients, for age group 2, 3, and 4. And let's use 2 degrees of freedoms for each of these two. Now we will go and look at the results. So here is the effect of female, here is the effect of age, and here is the effect of the 3 age groups. Here are the 4 splines for the baseline hazards. Here are the 2 splines for age group 2, so spline 1 and 2. Here are the 2 splines for age group 3, 1 and 2, and for age group 4. So 2 splines for each of those time varying coefficient variables. Again, we cannot tell much from the estimates, but we can keep the estimates, store them as time dependent too, and compare them to the previous model. And now we are looking at the effect of female and year. And now we will see something very interesting, that if either female or year were our exposures and age had been a confounding variable, does it matter if we put in a time varying effect on age? Here are the estimates for female, 0.59, 0.59 from the 2 models, and exactly the same standard errors. Here are the effects for years, 0.72, 0.72, and exactly the same standard errors. So clearly, adding in a time varying coefficient for a confounder is not necessary. Now, this is of course just one example, but I'm pretty sure that this is a general observation. So here is a question. Do you need anything to the data to prepare it for a time varying analysis? No, there's nothing special here. So don't confuse this with a situation where you have a variable that is changing values over time. For instance, a time varying exposure. Maybe I should talk about sex to make it very clear. If you're using the models I'm using now, you're saying that the effect of being female is changing over time. If you're using the other type of model, you are saying that someone is female for a certain period of her life, and then she changes to being a male. So that's quite a different situation. So no special data for this. Okay. We can look at the likelihood ratio test, comparing the 2 effects for age. And now we are sort of switching back to looking at age as our exposure. And that has a p-value of 0. So clearly a different model when we're putting in time varying effects for age. Now we can do the predictions, and they are exactly the same as we did up here. We predict hazards, everything set to 0 and per 1,000 person years into H1. And we do the same for age group 2 equal to 1, age group 3 equal to 1, and age group 4 equal to 1, and put them into their corresponding new variables. So these are called HT for time-dependent hazards, compared to the hazards up here with no T. And then I'm doing a plot with everything put into the same plot, and we can compare the results. So we get this very nice plot over here. The solid lines are from the proportional hazards model, the 4 age groups, and the dashed lines are from the time-dependent or non-proportional hazard models, again, the same 4 age groups. And you can see some differences in the hazards, particularly for the old group. There is a bit of a shift in the shape of the hazard, whereas for the blue group, virtually no shift. Our real interest, of course, lies in the hazard ratios. So let's take a look at those. Now we predict hazard ratio 2 using HR numerator, putting H group 2 equal to 1. And then that's always compared to 0, which is the same as H group number 1. This is H group number 3 versus group 1. And this is H group 4 versus 1, all of them with confidence interval. And then I do a plot of these over time. So here I have the 3 curves for the 3 age groups, hazard ratio of old people versus the youngest, hazard ratio of next old group versus the youngest, and so on. And they are compared to their corresponding model where I have fixed or where I have proportional hazards. And as you can see, they are quite different. Although without the confidence intervals put in, we cannot really decide if they're significantly different or not. But we know from the likelihood ratio test that they are different. It's difficult to put in the confidence intervals in a plot like this one because it gets a bit cluttered. But let's also point out that we see some very large hazard ratios up here. So this is 50, then we have 100, 200, maybe this is hazard ratios of 300 or something. Why are we getting that? We don't believe in hazard ratios equal to 300, do we? Well, that's probably because we have some hazards being very close to 0. So let's now do the hazard ratio alone for the oldest group, this time with confidence intervals. Now we see the effect, and now we can clearly see that the straight line here is outside the confidence interval. So this is deviating from a constant hazard. Why do we get the large values down close to 0? Well, let's take a look at the baseline hazard. And it has this shape. Now we can see that the baseline hazard for the oldest group is starting very close to 0. So we have hazards very close to 0. We're dividing by that, and that gives us these very huge hazard ratios that are not very meaningful. They're not wrong, are they? But they're sort of misleading in a way. How can we handle that? Well, instead of doing, let's see, where's the plot? Instead of doing the plot from time 0 and onwards, we could restrict the plot and plot from maybe half a year or for a year and onwards. That's one possibility. We could plot hazard differences instead, or we can just make a table of results from this one. I think I've done the latter here. Here I make a new time variable ranging from 1 to 10 years, and there are 10 values. And then I predict the hazard ratios on those values, contrasting group 4 equal to 1 to group 4 equal to 0. So that's the oldest versus the youngest group. And then fixing the values for female and for year at the same values and predicting on this new time variable. Let me show you. Yeah, I'm not sure. Let's not look in the data, but this is just showing some of the table results. And here we can see times 1, 3, 5, and 10 years, and the hazard ratios with confidence intervals. So this is showing you how to produce a table of results if you don't want to show the plot. Any questions or comments on this? It's getting late in the day, maybe. So let's see, what do we have left now? Back to presentation. So to sum up what we have done so far, we looked now at time-dependent hazard ratios for age. If our exposure was sex, well, then we get exactly the same estimate from the proportional hazard models as for the time-dependent model for age, meaning you don't need to put in time-dependent effects for confounders. And I think this is a general result. If, on the other hand, age is our exposure, well, then we need to show a plot of the hazard ratio over time or make a table of hazard ratios. And the huge hazard ratios that we saw were caused by hazards close to 0. We can do a plot of a restricted time from 1 to 10 years, avoiding time 0. And yes, and that's what we decided. So this is just to remind you of the result. These very high values over here were the result of the baseline hazard being close to 0 over here. Questions or comments to this? I just have to check how many are still present. Oh, we're still a good group here. That's nice. We are closing up till the end now. No, let's see, we are still staying here. I'll just say a few words on dose response modeling. We have covered that extensively in the earlier talks. So the idea is that we replace continuous exposure variables with splines to have something that's flexible. In this case, we don't have any margins command. It doesn't work after STPM2. So we have more difficult predictions, but you can use a downloadable program called XBLC. And I have never understood what XBLC actually stands for, so sorry about that. But you can do dose response plots using that one. And you can simply look in the syntax how that is done. Or you can use something else called Merlin with the spline object that makes it easier to handle dose response. Claudia is asking, does data have any export to Word functions so that tables like the HR table created can be inputted directly to Word? Yes, it has lots of functions for doing that. So one is, well, it has put Excel and it has put Word functions. And Stata 17 also has a new set of table commands. Very powerful, but very difficult to learn, I think. Okay, so I will simply skip the syntax. You can look at it in your own good time. Now, my last subject here will be problems with the hazard ratios. And this is sort of a sad but fascinating subject. It's also called frailty selection bias. Miguel Hanan wrote a paper in 2010 called what was it? The Hazard of Hazard Ratios. And it caused quite a stir because he was pointing out that there is an inbuilt bias into the hazard ratio. And let me explain what it is. So it's easiest to understand if we're looking at a randomized controlled trial example. We are assuming that we have a high risk of dying, and we also have a variable risk of dying. So we call that heterogeneity in the outcome effect, or in this case, it's often called the frailty. So we have frail people who die easily, and we have robust people who don't die that easily. And whether we have a high risk of dying, that depends on our situation. Whether we have frailty, I think in general, we always have that. So that's quite common. We also have a very strong treatment effect. In this case, it's a hazard ratio 0.5 for all subjects. So we have half the risk of dying if you treat it. And then at the baseline, when we have randomized people to treatment and no treatment, we will have a balanced setup. That means we have comparable groups. So all covariates or all variables will be equally distributed, including the frailty. We'll have just as many frail people in both groups. But then over time, this will not be the case. In the treated group, frail subjects will remain. They will die out, but slowly, because they are protected by the treatment. In the untreated group, however, frail subjects will die out quite rapidly. And over time, the treated group will have many frail subjects, and the untreated group will only consist of robust subjects. And then we have an unfair comparison between the groups. And this will affect the hazard ratio. It may go from 0.5, which is the true value, right after analysis time starts. And then over time, it will increase and can even go beyond 1, maybe to a value like 1.5, which is totally misleading. So this is an effect that is built into the hazard ratio. And of course, this was very disturbing to the world. Lots of people that I knew had spent their entire lives analyzing hazard ratios and doing theory on that. And of course, this was quite a shock when we realized that this was true. There were lots of other papers after Hanan showing the same effect. So you can accept this as a true effect. Now we are getting a bit further into time, and we have now come up with some alternatives to the hazard ratio. And one is to use the restricted mean survival time, or differences in this. And the other is to use standardized survival curves. And I'm going to show you the first one. And well, here is the original paper by Hanan. Here are some newer papers discussing this. And Stensrud is a Norwegian guy, so this is kind of fun. So, take-home message, use the hazard ratio with caution if you have a large and varying risk of event, or large or varying risk of dying, I think would be more precise here. So what is a restricted mean survival time? Well, that's a concept that's actually very easy to understand. Imagine that you'd like to look at life expectancy, and you're comparing Oslo West to Oslo East. People in the West live 85 years. People in East live only 80 years. So these are the mean survival times. The difference between them, 5 years, is then the mean difference. It's very easy to understand. people in the West live 5 years longer. Everybody understands that. So why do we talk about restricted mean? Well, that's because we have only observed part of the distribution, so we don't know the exact mean, but we know the mean inside of the data that we have estimated, and that's what we call a restricted mean. It's restricted to the max observation time. So if we look at Kaplan-Meier curves like this, then the restricted mean survival time is simply the area under the survival curve. So the area under this curve is the mean survival time. And then it's easy to see that the difference between treated and untreated will be the area between the survival curves. It's restricted to the observation time because we don't know what's happening very later. So therefore, calculating the restricted mean survival time difference at maximum follow-up is a very natural measure of effect, and it's an alternative to the hazard ratio. I don't know if you've thought about this, but a hazard ratio is actually very difficult to understand. If you try explaining somebody on the street what a hazard ratio is, I think people will find it difficult to understand. A restricted mean survival difference, however, very easy to understand. They live 5 years longer on the West in Oslo. Easy to understand. And the good thing is that this is not affected by the frailty bias that's affecting the hazard ratio. And as an extra bonus, it's just one number, also if you're using time-dependent hazard ratios or non-proportional models. So we have lots of benefits from using this one. So the only downside is that lots of people aren't used to seeing this one. So my advice is, show the hazard ratio, discuss whether you are in a situation that might be problematic, and then show restricted mean survivals and differences as an extra bonus. Now let's take a look. So now I think I'm skipping dose response modeling and interactions, and I go down to these problems with the hazard ratio. So now I am looking at my kidney data, where I have a very common death, and most likely we have frailty effects here. So my model is one where I include treatment. And as you may remember, we have a fairly strong treatment effect. Well, 0.74, not that strong, but a treatment effect at least. So let's look at the restricted mean survival time at maximum follow-up, which is 6 years. And let's calculate the difference using a command that's called stand-serve. And stand-serve stands for standardized survival curves. So standardized or marginal is the same effect or same concept. It means that we are specifying some variables that we contrast, and then all the others are simply taken over the values of the population or standardized to the population. So to do this, I generate a new time variable, and it's equal to the value 6, and I put that into observation number 1. So 6 years, that's the maximum follow-up time. That's where I would like to calculate the difference. Then I do the stand-serve command. At 1, I have treated equal to 0. At 2 is treated equal to 1. So that's the contrast that I'm interested in. Then I do this on time variable T2. So that's only one value here, 6 years. The contrast is the difference. I'd like to calculate restricted mean survival time. And the at variables are the new variables where this will be put into. And it's one called treatment 0 and one called treatment 1. Those are the new variable names. Then for the difference, I put that into the contrast variable, and that's called RMST difference. Okay, let's run it and take a look at the results. I think maybe I forgot to run the model. Let's see. No, we got results here. So let's scroll all the way out to the right side of our data. Yes. At least here we got the point T2 with an observation of 6. Maybe I forgot to run the model. Oh, variable T2 already defined. Okay, that was the trouble. So I just defined this one 2 times. Now let me run the stand serve again. See if I do better this time. Yes. So now let's scroll all the way out to the right. A bit further. Oh, there we are. So I have my new time variable. It's only one value. It's 6 years. Here is the expected survival time if you're untreated, about 1 year. Here is the expected survival time if you're treated, 1.4 years with confidence intervals. And here is the difference, 0.4 years with confidence interval. So here we have everything you need from that estimation. I can put it out in table shape if you like. Here's how I do that. And we can see that if you're treated, you're surviving 1.4 years. If you're untreated, you're surviving on average 1 year. And the difference is 0.4 years with a confidence interval. So this is the restricted mean survival time and its difference used for this type of model. Very easy to understand and not subject to the problems of the hazard ratio. Questions or comments on this? Let me see, maybe there's a message here I haven't seen. Thanks for good stuff. We'll have to go over it again. Yes, well, that I can understand. Okay, and also some other nice words. I'm guessing from this that people are getting tired. So I think we will just wrap everything up now. And let me go back to this one and talk about summing up. So I have shown you that the Cox model is a proportional hazards model, and it has some but a bit limited options for doing non-proportional hazards. The flexible parametric survival model is also a proportional hazard model in its standard version, but it has a flexible non-proportional hazards using splines, which is very nice to use. It can do lots of different predictions, hazards, hazard ratios, but also differences, and the same for survival and survival differences. And it can predict restricted mean survival time difference, which is a natural measure of effect that's easy to understand. And it's one number with confidence interval, also for time-dependent hazard ratio. So I really recommend using this. You will probably meet referees that are not used to it, but you will try to explain what it is and why it's a very good measure to use. And this one does not suffer from the frailty selection bias that may plague the hazard ratio. I'd like to end by saying a little bit about other features of these flexible parametric models. I said in the beginning that there is a whole ecosystem of models that are available to us. And this guy down here called Michael Croucher, he is the guy who's programming all these models. And he's a really good programmer, and that's why it's so much fun to use these models. So I'm just gonna go through it and, without commenting. You can do relative survival, you can do competing risk models, all inside the same framework. Joint modeling of longitudinal and survival data. You can estimate nested case control and case cohort data. Although in all fairness, this you can do with the Cox model as well. It's only requires weighted models. Multi-state models or event history analysis is possible, and it's very easy to extend the framework. You have simulation of survival data, something that I'm very happy about. And on top of this, you have Merlin, a unified framework for data analysis, and I'm just leaving that as a possibility. And these are my differences. Then, ladies and gentlemen, we are calling it a day. And if you have any questions at the very end here, please just shout out or type them in. And I'm thinking that maybe, okay, so some nice thanks for an informative lecture. Yes, that's very nice. Okay, then I will turn off the recording